Just a small moment. Okay, so the recording should be on. And welcome back, everybody, and welcome to this session on Physics 321. The topic this week is to start discussing the different types of conservation theorems and work and energy theorem, which we met on Monday. So on Monday, what we did was actually to present this work energy theorem with examples. And we discussed, we started to scratch the surface of some of these conservation theorems, but we also looked at some specific examples. Today, we are going to look at the conservation of energy. We're going to look at conservation of angular momentum. And we also, if we get time, we're going to look at the conservation of angular momentum. And one of the things which I wanted to do was to discuss in more detail parts of exercises 5 and 6. So 6 is the numerical variant of exercise 5. And exercise 5 is an exercise where we have a falling object in one dimension only. And on Friday, we are back into the STEM building, and that's where we're going to solve the exercises. And then I'm going to sneak in some roughly 10-15 minutes. And for that session, we are going to discuss even more, a little bit more about the exercises 5 and 6. And feel free to ask about the other exercises as well. So on Friday, we are back into the STEM building. So today is the last session, which we are going to do via Zoom. And on Monday next week, we are all back in the STEM building with regular lectures. So what we did on Monday was actually to derive this work energy theorem, which plays a very important role. And if we just scroll down a little bit, what we did was to start with the definition of the kinetic energy. And with the definition of the kinetic energy, we assume then that the forces depend on the position, the velocity, and time. Later, we are going to see that what we are going to label as conservative forces are forces which will depend only on the position. In addition, the curl of the force, which I'm going to define again, is a quantity which has to be equal to 0. And we are coming back to that a little bit later. We're going to show this mathematically that this is actually the case. So the thing we did on Monday was just to rewrite the kinetic energy. And we used this exercise 3 from homework number 1. And we calculated the derivative of the kinetic energy, with, in this case, just the velocity with respect to time. We also assume that the masses of the objects are actually time independent. So mass does not change. And then we could rewrite the derivative of the kinetic energy in terms of a force. If we now recognize this dv dt times mass as mass times acceleration. And then we had the velocity here, which again, we could rephrase in terms of a displacement, a change in the displacement. So what we have is a force acting on a line segment in a time interval delta t. And typically what we did next was to discretize, because obviously everything which we measure is something which is discretized. So we changed the infinitesimal quantity dk to a delta k, and same with time, same with position, and then the same with the velocity. And then we could manipulate this equation here with delta k over delta t, which we now could rewrite. If we now took v here, we know that v is the same as delta r divided by delta t. We know that this term here becomes the force. So we could rewrite this as a delta r over delta t times a force. And then we multiplied away the delta t here. And then we could show that the change in kinetic energy is given by the force which acts on a displacement delta var. Then we can collect all these small displacements. And when we collect them, we look at the difference between the final kinetic energy and the initial kinetic energy. And then we could change this one into an integral where we assume that delta r goes to 0. And that means that we could change this one into an integration from a position r0 to a final position rn. And this is the work energy theorem. And we looked at examples last Monday where we could actually use the work energy theorem. when we knew the initial velocity and the initial position and the forces, we could use that actually to calculate the velocity of an object if we know the forces and the initial velocity. And this gives us an additional recipe by which we can calculate things like the velocities and eventually the final position as a function of time in cases where we cannot integrate the equations as we've been doing before. Now, what we are going to do now, so this is one of the examples which we looked at, and we could find the velocity in that specific case, and this is roughly where we ended. There was another example which we looked at on Monday, which dealt with harmonic oscillations. And there again, we found that we could rewrite this in terms of the kinetic energy at the final position x plus the potential energy. And this was given by the potential and kinetic energies at an initial position and velocity. And this is a quantity which we now would use to say that energy is conserved. So this will be the final energy, kinetic plus potential, which is equal to the initial potential and kinetic energies. And these are equations which we are going to play around with quite a lot in the coming days and coming weeks. Okay, so what I wanted to do now is to look at some of the specific quantities which we put up last time, like the definition of an energy or conservative force. And then we are going to look at the conservation of linear momentum and angular momentum, because these are quantities which become very important in the analysis of a physics case, because that is something which will tell us something fundamental about the forces which are at play. So what I'm going to do now is just to change back to the whiteboard after this review of what we did on Monday. And then what we are going to look at now are examples and definitions of conservation laws. So let's just put this up here. So what we have, which we discussed last Monday, so we would define the total energy of the system in terms of the kinetic energy, K, plus the potential energy. So this is the letter which we're going to reserve for kinetic energy, an uppercase letter K. And then we have a V, or as it's in the textbook, you may find this referred to as U, but I'm going to use the letter V here. So this quantity here is the potential energy. And when we deal with conservative forces, there are some definitions which we are going to rewrite again and which we mentioned on Monday. So conservative forces, they lead, amongst other things, to the conservation of energy. So conservation of energy, of the total energy, means that if I look at the energy as a function of time, then the temporal change of energy is equal to zero. So this is another way of stating that this is a conserved quantity. Now, there are some specific things which we are going to study again and again, and then we're also going to derive this. So such a force, in order to have a conservative force, so this is the specific mathematical properties which they have to obey. So one is that the force itself is actually a function of r only. And we know an example already. We have the gravitational force. That's a typical example of that. Then another thing which is important is that the curl of the force is actually equal to zero. So if we do this in 3 dimensions, let me just quickly set it up here. So in 3 dimensions, that means that you would have the x component, and that would have the derivative, the partial derivative of the force with respect to the z component, and then I have the y component of the force minus the derivative with respect to y of the z component. Then I have the j vector, which is the vector in the y direction, and this has a d of x, and it has a derivative of f of z minus the derivative with respect to z of f of x. And finally, I have the last term, which is given by k. And then I have d of dy of fx minus d dx. It's actually dx here first. Sorry for that. This is a dy dx f of y minus a dy of f of x. Now, the next thing, which we haven't stated yet, is actually that this force, the force which we have, when we have a conservative force, that is given by the gradient of the potential. And the potential may depend on r, or it may just depend on the absolute value of r. So these are three very important relations which we are going to use again and again in the analysis of physics problem. So just a quick question to you guys. Would this curl of the force, this is a quantity which we want to be equal to 0. What happens for this curl, this quantity, if I just have a force which acts in one dimension? And it depends only on the spatial degrees of freedom, which means it depends on x or y or z. So what kind of result would you get if you have, suppose now that you have only, so this is the question related to point 2. Suppose I have a force F, which is now just a function of f of x, like the potential, which comes from a spring acting on a block. What would the curl of this force be like? So if I now write it, so this is F times I, so we have the vector I here. So what would be the curl of this quantity here? And you don't need to calculate here, actually. So if you're in one dimension, what happens to the curl of a force? Any good suggestions? So let me see in the chat here. Perfect. It's actually the roundest number you can get. So this is exactly equal to 0. So if you have a one-dimensional force and it depends only on the spatial degrees of freedom, then this is a force which will have a curl equal to 0, and it's going to be a conservative force. So if you look back at the case we had on Monday with a block which was sliding back and forth, and there was no damping due to friction, so this object would just oscillate back and forth in a very boring way. It's almost like my voice, actually. And in that specific case, energy will be conserved. And we saw that on Monday. So these are very important properties. Now, let's just go down a little bit. And now what we are going to look at, as we anticipated on Monday, is the conservation of linear momentum. And this is a very important property of linear or just momentum, as we said. So let's take a closer look at that. So we know that the total force which acts on a specific object or in a specific system. So if we now just write this as the total force, total, this is the sum of all the individual forces. So if we have now a given number of objects, so we have n objects, this is going to be given by the mass of this specific object multiplied with the acceleration. So if we are looking at, let's say, the solar system, the total force which is acting on the solar system would be the forces which come from every single planet plus the sun and the moons, obviously. Now we would now rewrite this in terms of the forces which we just of the each object which we have, and this object or these objects, each of them have one, there is an external force which we write like this. We haven't specified it. So this external force could, for instance, be friction. And then we have the internal forces. So if this object is interacting with another object with gravitational forces, for instance, then we would have an internal force. If we're looking at the solar system, we would have a force which acts on the Earth from Jupiter a force which acts on the Sun, from Earth, from Jupiter, from all the other planets. So if we look at this quantity here, this is now going to be a sum over all the other objects except the one which we obviously are looking at. There is no self-interaction, obviously. It would be horrible if we were to interact with ourselves continuously. And so there is no self-interaction, and that's why we have this J different from I here. And then what we have now is a force which acts between the two objects. So if you think of the gravitational force, for instance, so an example of a gravitational force is the term which we have here, m times the Sun times the Earth, and then we would have divided by the distance, the relative distance between the Earth and the Sun. So this is the absolute value of the radius of the Sun minus the, not the radius, but the position of the Sun minus the position of the Earth. And this quantity here is now to the power of 3. So it's 3/2 actually. And this is multiplied with the relative distance between the Earth and the Sun. And we would have an R, Earth and Sun. And this would play the role of I, and this could be J, and this would be I and J again. So this is an example of such a force which acts between two bodies. And we are going to meet that again and again in this course in particular. Now, suppose now that we have this n equal to 2 only. So we have two objects. So that means that this internal forces, when we look at it, is an I equal to 1 up to n equal to 2 here of F of I internal. And this is again, when we write it out, it's an I equal 1 up to n equal to 2 here. And then we have a sum of a j, but j has to be different from I up to n equal to 2 here. And then we have f of ij. And if I write this out for the case when n is equal to 2 here, what I get now is that f1 of 2, and then I get f2 of 1 here. Does everybody agree with that? Does that sound reasonable? Any questions so far? So I'm just rewriting this specific term here. Now, if I now think of Newton's second law, Newton's third law. If I use that, Newton's third law, what happens to this sum over internal forces? Any good suggestions from you guys? Fantastic. Thanks so much. This is again equal to 0. So you may have a kind of feeling that when I use this kind of voice, I'm actually looking after the roundest number you can think of. So again, this is equal to 0. And that is simply because we know that F12 is equal to minus F21. So this is just an application of Newton's third law. So if you now look at a case where we have n equal to 3, so let's do that case as well. So then we would simply sum the internal forces. So we would have I equal 1 up to 3, and then we have J different from I up to 3, and then we have our Fij. Then we would get first F12 plus F13. We obviously don't have an interaction between 1, 1. We have no self-interactions. And then we get, when I becomes 2, we have F of 2 of 3. And then we also have plus F of 2 of 1. And finally, when I is equal to 3, we get a final contribution, which is 3, 1 plus F of 3, 2. Now, if you look at this expression here, you can actually rewrite the whole sum here So if we now take the more general case with I equal 1 up to n, a general n, and we sum up all these interactions, this is now going to be equal to I equal 1 of n, and then we have j different from I up to n, and then we have fij here. And we can rewrite it. If you now look at the expression which we have here, we can now rewrite it in a slightly modified way. And this is what makes this a little bit handy, and we can show that immediately this is going to be equal to 0. Now we see that here because we know that this force here is equal to minus this one is equal to minus this one, and that one is equal to minus that one. So it sums up to 0. But we can rewrite this equation now as a sum over I and j. This is a double sum, and we have a constraint that I cannot be equal to j, and I can write this as f of ij plus f of ji. So what I've done here is just to generalize what I had in here. So this is essentially just a rewrite of that. And these forces are opposite to each other. We have a factor of a half in order to avoid this kind of double counting, obviously. And this is something which we then can rewrite in terms of the following expression. So we can now, if we take away the factor of a half, we can rewrite this. So these are just manipulations with summations here. So I would have a sum from I equal 1 up to n. I take away the factor of a half, and then you would typically have j larger than I, and then up to n, and then I have f of ij plus f of ji. And we know then from Newton's third law that f of ij is equal to minus f of ji. So that means that this sum over all the internal forces, and we have assumed that we actually have only a two-body force, so it acts on between two bodies at a time, this is actually equal to 0. So that's a very important result. And we have simply used Newton's third law here. So if you now look at what we have, this is something which we now can study in terms of the total momentum. So if you look at the total angular momentum, this is just the sum of the individual contributions. So we have n particles, and this is going to be given by the different objects multiplied with the velocity. So remember now that momentum is actually the mass multiplied with the velocity. And this is given by I equal 1 up to n, and then I would have lowercase p of I. So these are the individual momenta, which then add up to the total linear momentum. Now, the other thing which we now have to, which we need to do now, if we take the time derivative of the total, and then we take a dt here, we now have assumed that the masses are time independent. So that means that when we take the derivative here, we are just having mi, so this is unchanged, it's time independent, and then we have a dvi dt here. So this is now something which we recognize. So if you look at this expression, what we have here, what is this actually? If you look at that expressions. Any good suggestions? Let me see what's in the chat here. I mean, you guys are fantastic. So this is the acceleration times the mass. So that's the force. Excellent. So what we have here now is the force. So we would rewrite this as an I equal 1 up to n, and then we have an mi, and then ai here. And this is obviously now the total force which is acting on a specific object. So if we have I equal 1 of n, and then I have an mi, and then I have this fi, and now I have to be a little bit careful here, because I need to write this as the net force. So the net force, if we now remember what we defined a little bit earlier, this is given by this net is given by F of I external plus the internal forces. And if you remember what we discussed in the very beginning of the semester, we defined the forces as long-range forces, and these would typically be the internal forces. And then we had the contact forces like friction, the normal force, etc., etc. And these are forces which we normally would call as external forces. But they don't need to be only that. You could have an external force due to a particle which is moving in a specific field. So that could also be an example of an external force. So the external force doesn't need to be a contact force only. So it could be a particle which moves in a gravitational field. Now, if you now assume, if we make the assumption that this Fi net is equal to the Fi internal, if we do that, and then we perform the sum over all these, sorry, I actually was a little bit in a hurry here. This should not be here. This is just the sum over the forces here. Sorry for that. I saw it now. So if you see things like that, please don't hesitate to tell me. Now, if you now look at this, what I have is if I assume this, we know that what we have then is a sum over I equal 1 over all the internal forces. And if we then assume that the internal forces are of the type which we put up here, so that we can use Newton's third law, then we know that these internal forces are equal to 0. So that means that these are equal to 0. Again, everything is equal to 0. And that means that the time derivative of the total momentum, the linear momentum, dt is actually equal to 0, which again means that total linear momentum doesn't change with time. So momentum is conserved. And that's also a very important conservation law. So normally conservative forces, if you have conservative forces only, they will also conserve angular momentum. So what we say then is that the linear momentum is a constant of the motion, since it's conserved. So we would typically call this a constant of motion. Now we have to be a little bit careful. So if the external force, if we have an external force, so suppose now if this Fi net is actually equal to Fi, so the external force is not equal to 0, plus the F of I internal. If we plug that in again, then we know that when we are summing up here, is that the total force is now the sum over all the particles or objects which we have, and that's going to contain an Fi external plus the Fi internal. And we know that the sum over the internal forces is equal to 0, but this becomes equal to simply the sum over the external forces which act on each object. And that is different from 0, and that means again that the quantity of the total linear momentum is not a constant of the motion. Okay, so these are very, very important quantities which we are going to see again and again when we are going to study physics cases with conservative forces. And as far as we know, basically all fundamental forces are conservative forces, and they will conserve angular momentum, they're going to conserve linear momentum, and they will also conserve energy. So when we have these conservation laws, we can actually infer something about the forces which are at play. Now, there's one thing which I wanted to add. So in the first part of this lecture, we are going to look at some technicalities. And the next part deals actually with the angular momentum. So let's do that. Any questions, by the way, so far? Is this trivial? Is it obvious? In exercise, in homework number 4, we are going to play around with these conservation laws, because these laws play a fundamental role in the analysis in mechanics. Any questions so far? Is it everything okay? You may have seen this before, and I apologize for that. But I just wanted to have everybody at the same level before we really start to analyze physics problems. So the next thing I wanted to introduce now is the angular momentum. And this is also a very important quantity because it tells us if this is conserved, that means that we will have some symmetries in the potential energy. And one of these symmetries, which is then conserved, is a symmetry which is called rotational symmetry. So that means that you can rotate your system, but quantities like the energy, the angular momentum, and the linear momentum, they will just stay the same. So if you now are in a three-dimensional system, suppose now we define the x and the y and the z axis. So we place ourselves in a three-dimensional system. We have the x-axis here, we have the y-axis, and then we have the z-axis. So what we could do now is simply to say that the linear momentum is defined along the y-axis and the position is defined along the x-axis. So this is r. And if you now take the cross product of this will define a vector which points perpendicular to the plane, which is spanned by r and p. And this is going to be the angular momentum. That's the definition of the angular momentum. So what happens then is that when you have a velocity and a position for your system, and this frame is rotating, the angular momentum is then a vector which stands on top of the plane, which is spanned by position and the linear momentum. And then if this angular momentum changes with time, that means its time derivative is non-zero, then we are going to have a torque, which is perpendicular to the plane which is spanned by r and p. So the angular momentum is defined in terms of this letter L as an r times p. So this is just a cross product. And then we want to see now whether this dl dt is equal to 0. And which conditions we do have for having it to 0. So let's now make the calculations. And now we need exercise. So everything comes back actually. Exercise 4 from homework number 1, the first homework. So we need to calculate dl, and remember now that the masses are time independent. So what we have now, we can put the masses outside because we know that, sorry, I forgot one thing here. This is multiplied with the mass of the object because it's actually rotating an object. I forgot to put the m here. M, so we have m, and then we have to take the derivative of r dt cross v, and then we have the next quantity. We need to take r cross dv dt. And you remember in this exercise 4 in homework number 1, we actually looked at d dt of a cross b. And this is what I'm doing now, except that now a is replaced by the position and b is replaced by the linear momentum. Now, what we know is that the quantity you see here, this quantity, is actually the velocity, right? So this is the velocity. And we know that this quantity here is actually the acceleration. And we know also that when we take m is just a constant, so we can place the constant wherever we want. So what we have then is that we have m times a from the term here, and that's nothing but the force. So we can rewrite this equation in the following way. So we get this is equal to M times V cross product with V plus R with the cross product of F. So let me now ask you one thing. What is the cross product of the vector itself with itself? Let me see before we move on. Oh, sorry. This is you're right here. This is me. I'm confusing myself. There's a question in the chat here. I'm actually confusing myself. So sorry for that. I was looking at the next line. Thanks for stating that. So this is the same as M of R times V. Thanks. I'm very happy that you guys can point these things, because sometimes I'm just reading one line and then I write the next line. Thanks. Excellent. So if we now look at the expressions which we have here, if you look at this term here, can we say something about that term? Is this a term which we can get rid of? That is zero. I mean, if you take the cross product with itself, that has to be zero. So this is automatically zero. Now, the next term may not be zero. But let me ask you one thing. Suppose R is parallel with F. What happens then? If we just look at this specific case, that's also zero. Exactly. So if the force is parallel with R, then this term is also zero. But only if this is the case. Okay, so if not, so the first term is definitely equal to zero. I mean, that will always be equal to zero. And we can just leave it out. So if not, what happens then? Then this dl dt, which defines the torque, so that defines a vector here, a new vector, which is the torque, and that is equal to R times the force, or cross product with the force. And this is not necessarily equal to zero. So the thing which we're going to show now, before we go back to the exercises, in particular exercise number 6 for this coming homework, let's now see what happens if the force, so the total force, which we now looked at earlier, which contains an external force plus the internal forces. Let's now look at the case where this contains only internal forces. So let's assume that this external force is equal to zero. So this F, which we put in here, is actually this F of I, which we could have here. This could be the total force, or it could be just a force on a specific object. This is now something which is composed of external forces and internal forces. So let's take a closer look at that. And what we have now is obviously that this L is going to be the sum, since we are now looking at many objects. This is given by the sum over all the angular momenta for the different objects which we have. So that means that if I take the derivative of dl dt, this is going to be given by the sum over I equal 1 up to n, and then I'm going to take the derivative of all the small guys here, the individual angular momenta. And this, as we have seen, is actually equal to I equal to 1 times n, and then we have Ri multiplied with f of I, because this little guy here is simply the position of this specific particle multiplied with its force. multiplied with its, not the dl dt. Now, the next thing we need to do now is simply to plug in these internal forces. So now we look at the case where the external force is equal to 0. So we have internal forces only. So what happens then is that this quantity which we have, this dl dt, is now going to be equal to a sum over I equal 1 up to n, and I'm going to have an r of I, and we take the cross product, and we are going to have this sum over j not equal to I up to n, and then we have the sum over all these internal forces. So this is what I have, and this is something which I now can rewrite by the same trick which I used earlier. So I can rewrite this in terms of a factor of a half. So I'm just rewriting it in the same way as we looked at when we looked at the linear momentum. And this is a term which I now can split into Ri, cross product, with Fij. And this contains plus an Rj, and cross product with Fj of I. It's pretty easy to see that. It's the same trick which I used when I looked at the total linear momentum. Now this term, if we now follow Newton's law, this is the same as minus Fij. So what I can do next is simply to collect what I have, and I can rewrite this in terms of a half. I have a sum over Ij, and I cannot be equal to j. And then I can collect it in this way, because I have Fij is the same now, minus Rj, cross product with Fij. Now, if you then remember the gravitational force, so example, the gravitational force, that was given by something which is proportional. So this Fij is actually proportional to some constants and something more, but then it's proportional with Ri minus Rj. So what happens now if we now plug in the gravitational force, we are going to have Ri minus Rj, and then we have the cross product with itself. And what is this equal to? If we have such a force like that. Yeah, so today I am in the zero corner. So everything I'm asking about sums to zero, or is equal to zero. So this is again equal to zero. So that means that every contribution, if we have a force which looks like that, like the gravitational force, if we take the electrostatic force, the Coulomb force between two charged particles, that goes also like the relative distance, a vector which is given by the relative distance. And in that case, we have forces which are going to give zeros for every element in the sum here. So that means that what we get now is a dl dt, which is again equal to zero. So that means that angular momentum is also conserved, and the gravitational force is one of these examples. Now, what I wanted to end this lecture with is now a kind of way of just relaxing a little bit, and I want to go back to the exercises which we have for this specific homework. And in this specific homework, we are looking at an object which is now falling in 2 dimensions. Anyway, do you have any questions about what we went through now? So these theory demonstrations are important, and we are going to practice with these kind of theorems, the conservation theorems, next week in homework number 4. But unless you don't have any questions, I wanted to jump back to the Jupyter Notebook. So these are the slides for this week, and you have access to the Jupyter Notebook. And what I wanted to point out are the examples which you find at the end of this week's slides. So if you scroll down, you will see an example on how we can solve exercise 6. So what you will see here is basically what we had here. And in that specific exercise, by the way, this exercise 4 is something I want to discuss next week because that's related to the next homework. So I won't discuss it now, but I'm going to take this as an example about the talk next week. But what we had in this specific homework, if you now look at exercise 6, and I'm going to say something about exercise 5 on Friday, but if we look at this, we are now assuming that the object has a specific mass. I'm just initializing different packages. It has a given acceleration. By the way, there's a typo here, not two C's. Initial position, and it has initial velocities, which we can play around with. We will also discretize this in terms of a time step. So we have a final time minus an initial time divided by the number of integration points. Or you can specify delta t, and from delta t and the final time, you can find the number of integration points. So what we have here now is an implementation of Euler's method, which many of you have encountered. So we will simply have a loop over time, and at every time step, we update the velocity by multiplying this delta t with time. So this is an approximation. And then we will take the position, which now has Ri plus delta t times the velocity. And then we would calculate the new acceleration, and then we repeat these steps till we reach the final stage. So the first example which you see here, besides these initializations where I save figures, is actually an example of using a brute force division of the x and the y components. So I define these different parameters, g, and this parameter which is related to the drag force. There's an air resistance, the mass of the object. I define a delta t, I have a final time, and then I set this n as this ceiling where I take the t final divided by delta t. I define this constant vt as in the exercise. And then here I can define an array as a function of time for the v in the y, the velocity in the y direction. Same with position in the y direction, vx and x. And then I also have an analytic solution, which you're going to find in exercise 5. By the way, the analytical solution of exercise 5 is something you will find back, what we did 2 weeks ago, but it's also detailed in the textbook of Taylor. So you will actually find the analytical solution in the text as well. So if you're stuck, you can always look back to the lecture notes or in Taylor's textbook. But in this case now, we start integrating, so we loop through the time steps. And you see now that now I'm setting in the acceleration in the x direction, which now depends on the velocity in the x direction times the absolute value of the velocity, which contains the x direction and the y direction. This is why you cannot integrate analytically these expressions, because there is an dependence in the x direction on something from the y direction, and the same in the y direction here. So here I'm plugging in the accelerations, and in the y direction, we have gravitation as well. So you see minus g. And then we have the acceleration, which comes from the drag force or air resistance. And then I update the individual velocities, x direction, y direction, and the positions in the x and the y direction. I update time because I want to make a plot at the end. So time is now given by the initial times, or just this formula here, plus this delta t. And then I'm also plugging in the analytical solution. So in a sense, when you're looking at the homework, you roughly have the answer here, but I want you to play around and convince yourself that this is actually the way it should be. And then I plot the different results, and you will see now that I plot the y position as a function of time, I have the velocity in the y direction. And since I specified an initial condition here, as you can see, I defined that v of x is 0. That means that, and x is 0, so nothing happens in the x direction. And that means that in that case, I can compare everything with the analytical solution. So I'm using that to compare with the analytical solution. Now, the other thing which I will discuss a little bit more on Friday is the more compact version of what you saw here, because here we are simply defining x, y, and vx and vy, but you can write this in a more compact way using what we discussed in the previous homework. And this is something which I will say a little bit more about on Friday. And in that case, we can define a matrix for the velocity where we have time and the x and the y directions, and the same for position, which now has a matrix of time times the spatial directions. But now my time is over, and I don't want to abuse on your time, guys.